So the Inception network was created by Google, and they took, the name came from the Christopher Nolan film Inception, which came out about this time. And the motto is really, we can go deeper. And the deeper was in two different meanings. One was that the network itself can be deeper, but also the idea kind of we can go deeper, that we can have networks within networks. So they built up this building block, which is called an Inception building block. And their theory was, we're going to create some building blocks. We're going to be a little more agnostic about exactly what should happen at each layer of the network. We're going to give the network the opportunity to learn. So what we're going to do is we're going to go ahead and have some input. It's coming in. And it has some different options of what can happen. We can feed it into a one-by-one. Actually, I can say we can feed it into one-by-one. We're going to do several things. We're going to feed it into a one-by-one. We're going to also feed it into a 3x3, and these are all convolutions. So a 1x1 convolution, a 3x3 convolution, a 5x5 convolution. Notice there's not to scale since 1 and 3 and 5 look exactly the same size, but that's the idea. A 1x1, a 3x3, a 5x5, or a max pool. So this is a convolution, this is a convolution, and this is a convolution. And we're actually going to do multiple of these. So we'll actually have 128 kernels here, and for the 3x3, we'll have, let's say, 192. We'll have 96 of these, and we'll talk about the max pool in a minute. And what we'll do is then we'll take the output of these and concatenate them. And 3 of the 4 of these are going to be pretty straightforward. The max pool we're going to have to come back and look at. So we're not going to decide whether we should be doing a 1x1 or a 3x3 or a 5x5 convolution or a max pool. Instead, at each layer, we're going to do all of them. Right? This is kind of our building block Inception module. So let's say our input is something of the size 28 by 28 by 256, right? Then these guys are going to be 1x1 by 256, 3x3 by 256, 5x5 by 256. And again, we're going to come back to the max pool layer in a second. So if we look at the concatenation just of the convolutions, right, if we assume that these convolutions each have half padding and have a stride of 1, then the output of this convolution, right, is going to be something of size 28 by 28 by 128. So that's what's coming out of here. What's coming out of the 3x3 is going to be a 28 by 28 by 192. So we can go ahead and take the, let's just look at them. So this is 28 by 28 by 192. So this is from the 1x1, and this is from the 3x3. And if we look then at the 5x5 output, we'll get a 28 by 28 by 96. And this is from the 5x5. Well, we could just concatenate these together and end up with one large 28 by 28 by, whatever this is going to be, let's say we have 128 here, and we have 192 here, and then we have 96 here. So this is the first part, and then we add on this depth, and we add on this depth. So this max pool has a bit of a problem, right? This is actually, we're using a 3x3 max pool. The problem is twofold. One, normally if we use a 3x3 max pool, the size is going to shrink, right? In fact, if it's a 3x3, and we normally would use a stride of 3, we're going to shrink by a factor of 3. The second problem is even sort of more profound, and that is that our depth is 256, and the max pool doesn't change the depth, so that would stay at 256. So what that means is if we take their input, the depth is going to be, of the output, is going to be at least as large as the depth of the input. right? So the max pool takes the same depth as the input, and then we'd be adding on the depth for the convolutions. So that meant as we went from inception layer to inception layer to inception layer, we're getting deeper and deeper and deeper. And so we don't necessarily want that. So we need to deal with those two items, the height and width change, and we really don't want the depth to be this big. We'd like the depth, we'd like actually to end up somehow with a depth of 96. Let's see how we're going to do that. The simple thing we're going to do for the max pool for the 3x3 is just don't use a stride of 3. Instead, if we, for our max pool, let's say we have an input, which is 5x5. Now we want to do a 3x3 max pool. Okay, we would normally do a 3x3 max pool here, and then we would do sort of the remainder here, and so we'd end up with a 2x2. Instead, what we're going to do is, or maybe we'd end up with just a 1x1 because we'd ignore the output. Anyway, what we're going to do is instead of moving with a stride of 3, we're going to move a stride of 1. So the first, and not only that, we're going to use half padding. So our first max pool is going to be centered at the top left pixel, and then we're going to do another max pool here, another max pool here, another max pool here, and another max pool here. So we're going to use a stride of 1 and a padding of 1. I call that half padding, right? Because a half of 3 is 1. So that's how we're going to make sure that our height and our width are unchanged by our max pool. The max pool is still going to be doing some useful information, right? It's still going to be kind of telling us that some feature has occurred within these 9 pixels, centered, let's say, at 1, 1. And then some feature has occurred at the 9 pixels, centered at 1, 2, centered at 1, 3, centered at all these areas. So we'll still get this useful information. It's just somewhat different from the max pools we've been accustomed to, where our pooling partitions our input. And here we're going to have overlapping pools. The second thing we're going to do is we're going to add in a convolution after the max pool. Right? If we look at the output size of here, this is really, output is going to be 28 by 28 by 256, because we haven't changed the height and width and we're leaving the depth alone. So this is what the output is, and we want to get it to 28 by 28 by 96. So what we're going to do is use a 1x1 by 256 convolution, and we are going to use 96 of those. So we use 96 1x1 by 256 convolutions, and that will take our max pool 28 by 28 by 256 and take it to a 28 by 28 by 96. So now our concatenation can concatenate all 4 of these because they're all of compatible sizes, right? 28 by 28 by 128, 28 by 28 by 192, 28 by 28 by 96, and 28 by 28 by 96. And so we end up with a depth here that in this particular case like is around 500 something, right? So 200, 300, 400, yeah, this must be like around 512. So we've gone from a 28 by 28 by 256 to a 28 by 28 by 512. That's okay for this layer, right? Maybe we're just trying to double, from 256 to 512, but we could always just change these numbers to come up with the desired depth. Let's take a look at the number of weights in this Inception module. So we've got, for the 1x1, we've got 1x1, 1 times 1 times 256 times 128. So that equals 2 to the 8th times 2 to the 7th, so 2 to the 15th, which is about 32K. In the 3x3, we've got 3 by 3 by 256 by 192. So let's see if we can figure this out. This is around 500K. And then 5 times 5 times 256, so this is about 256 times 96 is about 25K times 25, which is around 625K. And then finally for our max pool itself doesn't have any weights, but we do have this convolution coming in here, right? Because we're coming in from the max pool into the convolution and then back out to our concatenation. And so here we've got 1 by 1 by 256 by 96. So this is around 25K. So each Inception module has about around 1 million params, 1 million weights. We can reduce this slightly. The 5x5 takes up quite a lot. Let's look at an optimization that we can do. So our total is around 1 megabyte, or let's say 1180K parameters. That's a lot. Let's see what we can do to reduce that. So what we're going to do is we are actually going to reduce the size of each of these convolutions. So instead of being a 3x3x256, we're going to reduce it. So we still have our 28x28x256 feeding in. And that can feed in directly to the 1x1 convolution. But before we go into the 3x3 convolution, we're going to actually add in another convolution. We're going to add in a 1x1 convolution, okay? And this is, of course, by 256. And how many of them are we going to have? We're going to have 64 1x1 by 256 convolutions. And then those 1x1 by 256 convolutions, the output of that will feed into our 3x3 convolution. So this will no longer be 256, it will be 64. Similarly, feeding into our 5x5, we're going to go to have another set of 1x1 by 64 convolutions. They're 1x1 by 256, and how many of them do we have? We have 64 of them. So we feed in from here, and that feeds into our 5x5s. So our 5x5s are no longer going to be 5x5 by 256, they're going to 5x5 by 64. So what we're doing is just doing some shrinking, right? Some reducing the size. So we're taking a 28 by 28 by 256 and we're turning it into a 28 by 28 by 64. So we are basically compressing in some way each of these. How are we doing this? We take a core through here, right? Basically one of these 28 by 28 pixels, and we go through and we get a core that is 1x1 by 256. And then we go ahead and apply our convolution to it. And that gives us an output. And we do that 64 times, and that gives us 64 outputs. So that's how, for every pixel, we're going to be getting a pixel that's 1x1 by 256 and turning it into a 1x1 by 64. When I say pixel here, this might be actual picture input, or it might just be some previous activation, but I'm thinking of it as pixels, right? So a 1x1 by 256, each one of these 1x1 by 256 turns into a 1x1 by 64. Let's just look and see what it does to the sizes here, right? So all of a sudden, the sizes turn into, the 1x1 doesn't change. The 3x3 layer, so let's look at the new. 1x1 is still 32K. The 3x3, we have two components. We have our new 1x1s, so this is 1x1 by 256, and there's 64 of them, right? So that's going to be 2 to the 8th, 2 to the 6th, this 2 to the 14th, so that's going to be about 16K. And then we also have now our 3x3 by 64, and we again still have 192 of these. So let's see, this is about 10 times 200 is 2,000. 2,000 times 60 is about 12,000, 120,000. Our 5x5, we've got again our 1x1s here by 256. And again, we have 64 of them. So we've already said that's around 16K. And then we also have 5x5 by 64, because we're now 64 deep, times 96. So this is about 2,500 times 60. So that's 2,500, about 25,000 times 6. So that's about 120,000. And then we still got our max pool at about 25K. So if we sum this all up, we've got about 120, 145, 160, 280, 300, 330K. So 330K is not bad. That's saving us about a factor of 3 over what we've got here. So each Inception module is going to be about that. So again, just looking at it, we've got our input. We go into a 1 by 1. We go into a 1 by 1, and then a 3 by 3, a 1 by 1, and then a 5 by 5. And then we go to a max pool. And from there, we go into 1 by 1. And then these all get concatenated together. That is an Inception module. There's one more thing that's actually done in the Inception v2 version, and that is we reduce the size needed for the 5 by 5s. So what the Inception v2 actually does is approximates a 5 by 5 convolution with two 3 by 3 convolutions. If we look at layer, let's say K, and we've got a 5 by 5 convolution, then if we look at the output of the 5 by 5 convolution, let's say we've got some output, and we look at some xy coordinate here. And the question is, what's its receptive field? That is, what are the pixels from the input, the 5 by 5 layer, that actually affect this? And it's basically a big 5 by 5 area around it, right? So we've got these values that are the receptive field, right? So if this is 1, 2, 3, 4, 3, then the receptive field is 2, 1, all the way to 2, 3, 4, 5, 6, 2, 3, 4, 5. So our receptive field is 2, 1, all the way to 6, 5. If, on the other hand, we go ahead and say we've got layer K and K minus 1, and then we have a 3 by 3 and a 3 by 3 convolution here, and we come up with the same output. Okay, so we have the same input, same output. What is the receptive field of this value? With respect to the intermediate here, right, to this level, it's 3 by 3. Right, so we have got, for that pixel, those 3 by 3. But now, with respect to each of those, what are their receptive fields with respect to the previous 3 by 3? Well, for every one of these, we're going to take a 3 by 3 bounding box around it, right? So if we look at this one at the top left, its bounding box is going to be this top left 9 squares of here. Okay, so if we look at the receptive field of 4, 3, which is this value here, at output of K minus 1, it's going to be 3, 2 to 5, 4. This 3 by 3 here. But now if we look at each of these, for instance, the receptive field of 3, 2 with respect to its previous layer is going to be 2, 1 all the way to 4, 3. So if we look then at the output of K minus 2, for each of these in this 3 by 3 value, it's going to get us to that same 2, 1 to 6, 5. So really what I'm saying is this value is dependent on the 25 values that are surrounding it in either the 5 by 5 case or two 3 by 3s. Now, we're losing some power in the two 3 by 3s, right? In the 5 by 5, we're going to just go ahead and take a convolution of all these 25 values. So we're going to do this weighted sum of all of the 25 values in the previous layer. Here is going to be doing something different. we're going to be doing a weighted sum and then another weighted sum. And we can't, for instance, we're not doing in the 5x5 case, we're looking at the top left and the bottom right simultaneously. Here, we're not getting that. The advantage is the weight matrix size. So the weight matrix size in the 5x5 is, of course, 25, where in two 3x3s, it's 9 plus 9 equals 18. So by replacing a 5x5 with two 3x3s right here, we can actually save ourselves and only use 18/25ths of the total amount. So that's what? That's around times 4, 36. That's around 70%, right? So a 30% reduction. So we would be able to reduce this size here by the 120K by about a third. So save another, what is it? 40K. So get our 330K down to 290K, which again saves us a little bit more. So an Inception network has something like 7 different Inception modules. So this is one module, and those 7 modules put together. In between those inceptions, so this is an Inception module, Inception module, and Inception module. Between these Inception modules, max pooling operations are done to reduce the dimensions, the height and the width dimensions. This is fairly deep, right? Because we've got, for each one of these modules, we've got several paths that are coming in here. So in addition, they do an odd training thing where they actually have the output here. I'm going to call this the real output. And then they have coming off some sort of fake outputs, 2 intermediate fake outputs. So this is intermediate 2 and intermediate output 1. So this is just what's coming out of this layer goes to here, and what's coming out of a higher layer goes to here. And what they do then is they put those through some big fully connected networks, and then a 1000 softmax. And the same thing here, through some big fully connected layers, and eventually end up with a large softmax. So what they're trying to do is deal with the problem. So in this real output here actually goes into a big softmax too. So we can think of our loss as composed of 3 portions. Our training loss equals the loss for the real loss, okay, which is how well does this do classification, plus the loss for output 2 and loss of output 1. Where the loss of output 2 is basically how well does this intermediate Inception layer do as far as solving our final problem, given we have these trained fully connected layers. And similarly, how good does even just like the second Inception layer do in terms of providing enough useful information such that we can train some fully connected layers in order to solve the problem. So we do, we don't treat these all equally. We do, let's say, the real training loss plus maybe, 30% of the output 2 plus 30% of the output 1. This is only used for training. And the reason it's used for training is to try and get gradient down to earlier parts of the network, right? This is a long path, and so it's hard to get gradient down here. It's easy for it to vanish as it's going back. So what happens is during our training, we're calculating the training loss. And if we look at the partial derivative of the training loss with respect to, let's say, Inc 1, that is the first sets of weights down in here. Well, we have several paths to get to Inc 1, right? We have the path from our final output layer and computing its loss and going down, but we also have the path from here and the path from here. And notice the path from here is actually very short, and so it's much easier to get gradient down to the first inception layer from this auxiliary loss. And similarly, we'll probably get more loss from this more gradient to Inc 1 from our auxiliary loss here than we will from here, because it's so long a path. So this is an unusual technique used, as far as I know, only by the Inception architecture of providing these auxiliary classifiers that are using activations part of the way through the network, trying to ensure that we are learning useful representations early in the network. This is only used for training, right? While we are actually doing prediction, we just ignore this part and just go straight up through our inception layers and out to the real output and to our final softmax. I'd like to look at this in a little more detail. How is it that the neural network learns to decide that it would like to use 5x5 convolutions at this particular layer? Well, it's actually decided at the next layer. So if we look at this layer, right, this layer, what we've got coming out is a set of activations, and we have portions of this, right? We've got the part that's the 1x1. We've got the part that's 3x3. We've got the part that's the 5x5. And we've got the part that's the max pool. So this represents the concatenated output from this layer. Now let's look at the next layer. In the next layer, we are going ahead and looking at these values, right, and doing convolutions on these values. And we are learning weights, determining what amount to take from each of these. So let's just look at our simple example. Let's look at the 1x1 in the next layer. Okay, so this is the 1x1 in the next layer. There's similar things happening with 3x3, but 5x5. The 1x1 in the next layer is also, we can separate into these sort of four parts. There's the parts that are dealing with the 1x1 from the previous layer, the parts dealing with the 3x, should be 3 of course, in the previous layer, the depth dealing with the 5x5 in the previous layer, and the depth dealing with the max pool in the previous layer. So let's say this particular 1x1 convolution, and remember we have a whole set of them, this particular 1x1 convolution decides, I really like max poolness from the previous layer. That's useful for me in doing my computation. So I'm going to have weights in the max pool area that are non-zero, and I'm going to use zeros for the 1x1, the 3x3, and the 5x5s. That's what this convolution decides. That's what it finds useful from the previous layer, the max pool parts. Another 1x1 might decide something different. So, right, this 1x1 might say non-zero, 0, 0, 0. We might have a different 1x1 kernel, whose weights, right, which are being learned, decides, I don't actually want the max pool. That is not useful to me as a convolution learning what I'm trying to learn. So it's going to go ahead and set the max pool to 0. It might say, I actually like a combination of some of these 5x5s and some of these 1x1s. So I'll make these be 0, and I'll make some of these some 0 and some non-zero. Some non-zero. And so it will be taking a weighting of some of these 1x1s and some of these 5x5s. So that is how we can actually use these 1x1s, 3x3s, 5x5s, and max pool. So it's not that we're saying at a given layer, this inception module is either going to be working as a 1x1, a 3x3, a 5x5, or a max pool. Instead, it's working as all of them. And on the next inception module, it can go ahead and utilize any of those that it wants, right? Any of these particular convolutions can go ahead and utilize any particular combination of the 1x1s, 3x3s, 5x5s, or max pools from the previous layer. Some kernels use some set of weightings, other kernels will be using different weightings.